Today we're going to talk about the difference between isotopes of an element and the effect that that has on the atomic mass of that element. Isotopes are different forms of an element with the same number of protons but different numbers of neutrons. For hydrogen, there are three stable isotopes of hydrogen: protium, deuterium, and tritium. Hydrogen mostly exists as one proton and one electron. But we can also add more neutrons to the center of the atom. This creates isotopes. All of the elements, or all of the atoms that we see here, are the same elements. They only differ by their mass number, which is changing the number of neutrons. In order to measure the mass of things that are extremely tiny, like atoms, we came up with the atomic mass unit. Carbon-12 is one of the most stable, common isotopes that exists. So what scientists did was they took the mass of a carbon-12 atom, they sliced it into 12 exact units, and we use that as a unit of mass when we measure the mass of subatomic particles and atoms. You can see in this table that the mass of a proton and a neutron is not exactly one atomic mass unit. The mass of a proton is actually a little bit less than the mass of a neutron. You can see that the mass of an electron, like we said, is about 2,000 times smaller than the other subatomic particles. The point being is that the atomic mass unit is just a very small unit of mass that we use to measure the mass of atoms. Atomic mass is a weighted average of the masses of individual isotopes of an element. Every isotope has a percent abundance of how much is in the universe. In the case of hydrogen, almost all hydrogen atoms, 99.98% of hydrogen atoms, look like this. But a few hydrogen atoms that we might find, about 0.02%, might have a neutron. Tritium is extremely rare. It's only found really in stars or in our sun. Another example of multiple isotopes would be the element strontium. Okay, so we have 4 stable different isotopes. Each isotope has a very, very exact atomic mass in atomic mass units that is determined experimentally. But you can see here that most strontium atoms, or 82.58% of them, are strontium-88. The next most abundant element is strontium-86. But if we go to our periodic table and we take a look at strontium, right? The atomic mass of strontium at the bottom of its symbol is about 87.62. It's closest to the mass of our most abundant isotope. Just like when you calculate your grade is mostly skewed towards your test score because tests are just worth more than your homework. The atomic mass of an element is a weighted average of the abundances of each isotope multiplied by their atomic masses. The reason why the exact masses of isotopes does not equal the sum of the masses of protons and neutrons and electrons in atomic mass units, right? So we have 2 protons and 2 neutrons, which should have a combined mass circled here. But inside of a helium nucleus, that mass is actually a little bit less than what we would expect. This is caused by something called mass defect. Einstein came up with an equation that said sometimes matter can actually be converted into energy. So when protons and neutrons connect together inside of the nucleus, some of their mass is lost in the form of energy, and that energy that is lost is called binding energy. The most important thing that we need to know is the mass of individual atoms very rarely will come out to be whole numbers in terms of their atomic mass units. How would we determine the average atomic mass of an element if we're provided the following information? Well, the atomic mass of an element is a weighted average. We have two stable isotopes of silver, silver 107, silver 109. We have their exact masses, and we know what the percent abundances of each of those isotopes is. The very first thing that I do is I take each mass of each isotope and I prepare to multiply it by the decimal version of each one of these percentages. When I find the product of each one of those masses times the percent abundance as a decimal, I add them together to get a sum. What I did here was I took the percent abundance of silver 107, I converted it into a decimal, and I did the same thing with the percent abundance of silver 109. I'm going to multiply these numbers together and add them. We'll maintain the same level of precision, right? We have 4 significant digits in our percent abundances, so let's round our average atomic mass to that level of precision. And if we do that, we get the average atomic mass for silver to be 107.9 atomic mass units. Now let's go back to our periodic table. If we go back to our periodic table and we find silver, silver has an average atomic mass that rounds almost exactly to 107.9. That's why this number is so important. It's most closely going to resemble the mass of the isotope that is the most abundant. Just like your grade in this class most closely resembles the percentages that you get on your tests, because your tests are simply just worth more in terms of their percentage. Here's a practice problem. What I'd like you to do is I'd like you to pause the video. Instead of 2 isotopes, we have 3. Here are the percent abundances of those isotopes. Go ahead and see if you can work out this problem yourself. We'll check the answer and see if you can identify what element we're working with. If I take the weighted average of all of these masses times their percent abundance, and let's round it to the level of precision of our least number of sig figs, I get an average atomic mass of 24.31 atomic mass units. Now, if I go back to my periodic table, I can actually identify what element this is, because if I find magnesium, it has an average atomic mass of 24.305 atomic mass units at the very bottom of the symbol. And if I go back to my work here, it looks like that matches what I just calculated. But what if we didn't know the percent abundance? Given the following information, determine the percent abundances of the isotopes of nitrogen. Now, I have 2 variables, which makes it seem as though I don't really have the necessary information to solve this. But there is one piece of information that is not listed here. If I go to my periodic table, I know that the weighted average should match what's underneath the symbol, which is 14.007 atomic mass units, and that's what I'm going to use as my weighted average. I also know that my 2% abundances should both add together to give me 100%. Or as decimals, those 2% abundances should add up to give me the number 1. This allows me to create a system of equations. I can treat the first percent abundance like it's x, the second one as though it's y. I know what my average atomic mass is because I can grab that from my periodic table. Now, even though I have 2 variables right now, we just said that x plus y must equal 1. I can then set up a system of equations to then substitute my variables back into this equation to solve for at least one of the variables first. Since I know that x plus y must equal 1, I can rearrange this equation to isolate for y, and if I simply subtract both sides by x, I get y is equal to 1 minus x. Then what I'm going to do is I'm going to substitute 1 minus x in for the variable y. Now be careful with the algebra for this next step because this decimal number becomes the coefficient of x. This decimal number must distribute to both the 1 and it must distribute to the negative x. The next form of this equation after I complete this distribution is listed at the top, and I'm going to use this equation to solve for x. First, I'm going to combine like terms. I'm going to take this term, combine it with this like term for x, and I'm also going to subtract both sides of the equation by 15.000108, and this becomes my new equation. Since both of these numbers are negative and I'm isolating for x, if I divide both sides of this equation by this negative coefficient of x, I get that x is equal to 0.9961. Since I know that both of these percentages must add up to give me 1, I can take 1 minus this decimal percent abundance for x, and I can find the other percent abundance, and then simply moving the decimal place over 2 spots, I get my new calculated percent abundances for both the isotope nitrogen 14 and the isotope nitrogen 15. Here's a problem that's very similar to the one that I just did. So pause the video, try this problem yourself, and we'll go over the solution momentarily. I'm going to set up my substitution the same way that I did. X plus y has to equal 1. I substituted a term in for y and I distributed my coefficient across. In my solution, I should have another negative coefficient of x, and I have a negative number over here. If I divide both sides by this negative coefficient of x, I get that x is 0.6915, which means that both numbers add together to give me the number 1. This should be my decimal percent abundance for the other isotope. Moving the decimal place over 2 spots, I get 69.15% for copper 63 and 30.85 for copper 65. Our next and final topic here is, well, how do we look at the periodic table and make some simple estimations as to what isotope is the most abundant? It actually doesn't even involve any math. Tin 118 versus tin 120, what I would do is I would go to my periodic table, find the symbol for tin. The average atomic mass is 118.71 atomic mass units, which rounds more closely to tin 118. So I know tin 118 is the more abundant. If I look for potassium on my periodic table, potassium has a mass that is 39.098. So therefore, if I go to my periodic table, potassium 39 is the most abundant isotope. Mercury, I can do the same thing. And if I go to my periodic table, the most abundant isotope is mercury 200. For these isotopes of barium, I go to my periodic table. The average atomic mass for barium is 137.33, so 137 has to be the most abundant isotope. For krypton, the most abundant isotope would be the one that matches or is most closely rounded to 83.8, and that would be krypton 84. And last but not least, we have chromium. Chromium's average atomic mass on the periodic table is about 51.996, so chromium 52 is the most abundant isotope. The average atomic mass is closest to the mass number of the most abundant isotope. Our final topic will be radioactivity, where it comes from and why it forms, and that will be our final lesson for this unit that we're on.